how do we represent this curvature effect at the level of metric? Remember, there's three levels. There's the Riemann curvature, the connections from which it's built, those gammas, and then the gammas are made out of the g's, the metric. How would we represent it at this level? We assume that the universe is homogeneous, isotropic, where it's the same everywhere. That's a basic assumption of cosmology. You can't prove it exactly. Now we have observational evidence that maybe might be true, whatever, complicated, but basically we can make that assumption here. Everywhere it's roughly the same, okay? But it's changing with time. So at any given time it's the same everywhere. The next instance is also the same everywhere, but a little bit different than it was before. A little bit further apart everywhere. Changing with time, but at any point in space at a given time it's the same. What would the metric look like? We'll write down a metric which we think corresponds reasonably to what the universe is like. Basically, so we have two pieces. We have time. What are we going to say? In that physical three-dimensional space, the distance between any 2 points is going to change with time. It's going to be a function of time. A function of time in front of the spatial part of the metric. Given any time, it'll be a certain way everywhere. The next time will be a little bit different everywhere, maybe a little bit further apart everywhere. Okay, so it'll be some function of time multiplying the spatial three-dimensional part of the metric. Okay, so look at the top upper left-hand side. You have ds squared. All right, forget about the dt squared part. Just look at the second part. You have r squared of t, some function of time, multiplying this whole spatial thing. What should be in front of the dt squared? Now, if we had a gravitational field, we saw previously, and you don't have to remember exactly now, but we saw that there would be a function of r in front of the dt. And that gives us the derivative of that with respect to the other coordinate, which is r, gives us the gamma, and that gives us the space-time connection, that gives us gravity. Here we're not talking about gravity, per se. In other words, the gravity created by some source towards which some particles are falling. We're talking about something different. We're talking about all the particles together in the uniform field created by all of them together. That's going to be contained in all this stuff on the right-hand side, the r of t squared, or the r squared, etc. In front of the dt squared, we're going to have nothing, just at -1, right? The -1 from special relativity. Friedman-Robinson-Walker solution, which is the cosmology solution that gives you the expansion of the universe, a metric which we think corresponds reasonably to what the universe is like. And we'll solve the Einstein equations for that unknown, one unknown, basically a function of time in front of the spatial part of the metric. Remember, we spoke about the fact that the existence of this substructure makes things much easier. We can do computations much more easily, and we can also visualize things or write things down just given a symmetry. Like we know it's spherically symmetric, we can immediately write down a metric in a certain form that has very few g's in it. Whereas we would not know how to do that necessarily just writing the r's or the gammas right away. So the existence of this structure enables us to do things very quickly. Okay?